Hello friends, welcome back to our channel. So in today's session we'll discuss about one more concept in operating system, that is a demand paging. So in our previous session we have seen what are the pages, what are the frames, and how to convert a logical address to the physical address, and also we have seen different types of structuring the page table. So now we'll see the virtual memory, which is a demand paging. So demand paging. So paging, we know about this paging concept. So the primary memory will be divided into frames, and the logical memory will be divided into pages. So the CPU will be executing only the process which is available in the main memory. So the pages of logical memory will be loaded into the frames of primary memory. Okay, so that the conversion of logical address with the physical address that we have seen. See, here demand paging, the name itself indicates demand, means so not executing all the pages or not loading all the pages into the main memory. So with the demand from the CPU, the required pages only be loaded into the main memory from the secondary memory. See, so the main reason for this demand paging is to optimize wastage of memory. To optimize wastage of memory, so the memory will not be wasted. So why means, because so here you can see this is a logical address, for example. So this is a process, okay, and this is a process 1, okay. So for example, the process 1 is having some 4 pages, okay. So let it be page 0, page 1, page 2, page 3, and for example, let it be this is a page table. This is a page table, okay. So we know that the page table will be having all the entries. So page table of P1. Similarly, let us take one more process. So 3, that is a page 0, page 1, page 2. This is a process P2. Okay, so in order to avoid the confusion, let us take this one as page 4, 5 and 6. Okay, there is no continuity. Just to avoid the confusion, I am giving the unique page names. And this is a page table of P1 and this is a page table of P2. Page table of P2. Now, this is the main memory where we have to store the pages. This is the main memory. Okay, so for example, this particular page table will be divided into 2 columns. So we know that the page table will be having the corresponding frame numbers. So we have studied that in our earlier sessions. So this page table will be having a frame number which points towards the location at the primary memory or a main memory. So apart from that, there will be a lot of bits, and in that the additional bit is, and this portion is valid or invalid bit to represent the status, okay, valid or invalid, okay. Similarly here also this is a valid or invalid, so which is represented as valid as V, invalid as I. Here also valid as V, invalid as I. And here there will be a frame numbers. So let us take this one, frame numbers. Let us assume these are all the different frames, and we know that the frame size is equal to the page size, okay, to fit it. So let it be, this one is a F0, F1, F2, F3, 4, 5, 6, 7, 8, 9, 10 and 11, for example, right? Now the page numbers, for example, it doesn't mean that we have to store all the pages in the main memory, okay. all pages should be loaded in the main memory. So if demand paging, the name itself indicates, with the demand of CPU, only the required pages will be loaded into the main memory. For example, among these four, let us take, so this is a page 0, page 1, page 2, page 3, and here also page 4, page 5, page 6. For example, this is a invalid, this is a valid, valid and invalid. For example, this is at F1, F3, and here it is a valid, invalid, valid. Okay, let it be, it is at F4, F11, sorry, invalid, no, so F11. So that implies valid means the page is already available in the main memory. So F1, so page 1 is loaded here. So it is a page 1, and page 2 is loaded at F3. So here it is a page 3, and here page 4 is loaded at F4. So this position page 4, and F11 it is stored at page 11. So like this, so you can observe here, totally two processes are there, and among these two there are total 4 plus 3, 7 pages are there, and here we are in the main memory, there is no 7 pages loaded, only the required pages are loaded. So only page 1, page 2 from process 1, and page 4 and page 6 from process 2, only these pages are loaded. So there is no wastage of memory. Okay, so whenever the CPU demands for a page, so the page will be available, so it will check in the main memory. So now see, when if the CPU wants to execute, for example, page 3, okay, page 3, if CPU wants to execute this page 3, so once again I'm saying CPU will be executing only the process from the main memory. So first it will check in the main memory. So CPU checks for page 3 in the main memory. So how it will check? So it will be checking in the main memory. So if the page is not available, so here you can see, sorry, page 3 is available. So this is a page 2, because this is a page 2, page 2. So page 3 is not available in the main memory. So if the required page is not available in the main memory, which was demanded by the CPU, that we call it as a page fault. Okay, so page fault. Page fault. So page fault means whenever the CPU demands for a page which is not available in the main memory, then it is called as a page fault. So if there is a page fault, what happens? So immediately the CPU will be transfers a control, okay, the trap control or trap system call to OS, okay, to OS, to the operating system. So CPU will be transfers a control to the operating system that there is a page fault. Page fault means the required page is not available in the main memory. Then immediately the OS will copies or load page 3 from secondary memory to free space in main memory. So this happens. So first the CPU will be demanding for some page. Okay, the CPU will be demanding for some page, and if the page is not available, then page fault occurs. And in order to handle this page fault, the CPU will be transferring a control to the operating system by conveying that there is a page fault. Immediately the operating system will load the page 3 from the secondary memory, because the complete pages will be available in the secondary memory only. By the demand of CPU only, we are loading the pages to the main memory. So P3, the page 3 from secondary memory, SM means secondary memory, to free space in the main memory. So what happens? Let it be, this is a free space. So page 3, okay, it will be loaded here. Then what happens? The page table will be updated. So the page table will be updated. So because the page table will be having all the entries of the pages which are loaded in the main memory. So the frame number is F7. So F7 will be kept here and this invalid will be modified to valid. Okay, this what happens. And after updating this table, so the instruction or a page will be re-executed. So the page will be re-executed by the CPU. The page will be re-executed by the CPU. Okay, so this happens when page fault occurs. Okay, whenever the page fault occurs, this is the process happens. The CPU will be transferring the control, OS will be loading the required page from secondary memory to the main memory, and the page table will be updated, and then, so this will be reference. Okay, and then the page will be re-executed by the CPU. Now, there is a one more question. If, for example, these are all also filled with some other processes. Okay, now you can observe the complete main memory has been filled with all processes. Okay, for example, there is a one more process. So let it be some P10, and here there is a P11, here it is a P12, and here is a P13, and here it is a P14, and here it is a P15. For example, let us imagine that. So the main memory is completely filled with all the pages. There is no free space. So what happens here? See, whenever there is a page fault, for example, CPU now requires to load page 0. Okay, page 0 to the main memory. But you can see the complete main memory is filled with the pages. There is no entry. So what happens here? So automatically the first step, that means it will transfer the the trap to the operating system. Now the operating system finds that the main memory is completely full. Now what happens means, now it will happen the swap in process and the swap out process. So this we have already discussed in our previous sessions, swap in and swap out. So first swap out will be done. Swap out means whatever the page completes its execution, that page will be removed from the main memory and it will be loaded back to the main secondary memory. For example, page 11 completes its execution. So page 11 will be removed here and it will be transferred to the secondary memory. Now there is a free space. So this process we call it as a swap out. Okay, the page which completes its execution, the page will be moved to back to the loaded back to the secondary memory from the main memory. So now there is a free space. Now the CPU will be loading page naught from the secondary storage to the main memory. So this is called swapping. Okay, loading the required page from secondary memory to main memory is called as a swapping. So these two processes will be done when the memory is full and CPU still wants to execute a required page. So there is no memory in there is no free space in the main memory to load the required page from secondary memory to the main memory. So then the swap in and swap outs will be done. So swap out will be done. So the page which completed its execution will be immediately loaded back to the main memory, moved back to the main memory. So swap out. So obviously the main goal is optimizing the wastage of memory. So instead of loading all the pages which is required or not required, so loading only the pages whenever it is required. So the CPU demands the pages which are going to be get executed by the CPU. So only those pages will be loaded from the secondary memory to the main memory. If the page is not available, page fault will be occurs. So we are going to handle this page fault. So page fault will be handled. So by sending the control to operating system, and it will be loaded from the secondary memory to the main memory. It will update the page table, and finally the complete instruction will be re-executed by the CPU. So this is what happens in the demand paging, and it's also known as virtual memory. Virtual memory, right? So because the complete process not loading into the main memory, still we are executing the complete process. Okay, so that's why we are calling it as a virtual memory, right? So hope you understood this concept, and if you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.